So we're going to start the proof for the Lagrange error bound with a few definitions. The first definition is that the error is defined as E of x is f of x minus p of x, where p of x is the nth degree power series of f of x centered at a. So f of a is going to be equal to p of a, and E of a is going to be equal to f of a minus p of a, which will equal 0 because they're equal to each other. You can follow this to determine that f prime of a is going to be equal to p prime of a, and e prime of a will still equal 0. The same follows for the second derivative. This set of equations comes from the definition of a power series centered at the point A. And so from this, we can get the more general equation, where p to the n plus 1 of x is going to be equal to 0 based off of the definition of the n plus 1th derivative of an nth degree function, where it will always be equal to 0. An easy example would be the second derivative of y equals x, where y double prime is equal to 0. You can see that e to the n plus 1 of x is equal to f to the n plus 1 of x minus p to the n plus 1 of x. And so e to the n plus 1 of x would just be equal to f to the n plus 1 of x. So one more definition here is that the absolute value of f to the n plus 1th degree of x is going to be less than or equal to m, where m is the maximum value of f to the n plus 1th degree of x over the interval a to b, over the closed interval a to b. And so you can combine this new definition with the definition we just found, where the absolute value of e to the n plus 1th degree of x is equal to the absolute value of f to the n plus 1th degree of x, and both of those will be less than or equal to m. And so for this definition, we'll find that the absolute value of the integral of e to the n plus 1th degree of x dx is less than or equal to the integral of the absolute value of e to the n plus 1th degree of x dx. This can be found because if e to the n plus 1th degree of x has positive and negative values on a graph, then the area under the curve is always greater when the absolute value is inside the integral. If the absolute value is outside of the integral, the area under the curve will simplify itself out. This leads to the inequality in the beginning of this step. Using this, you can take the definition that we just found and say that the absolute value of the absolute value of the integral of e to the n plus 1th degree of x dx is less than or equal to the integral of the absolute value of e to the n plus 1th degree of x dx is less than or equal to the integral of m dx. And you can take out the middle term there to find that the absolute value of the integral of e to the n plus 1th degree of x dx is less than or equal to the integral of m dx. You can take this, and when you solve the antiderivative, you'll find that the absolute value of e to the nth degree of x is less than or equal to mx plus c, because there are no bounds on the integral. So what you're going to want to do is solve for c here. And doing this, you're going to want to do it where the error is 0. And so first, you're going to plug in the point a where the error would be 0. And so the absolute value of e to the nth degree of a is less than or equal to ma plus c. Setting e equal to 0, you get 0 is less than or equal to ma plus c, which you can simplify into c is greater than or equal to negative ma. Ignore the less than or equal sign. C is greater than or equal to negative ma. And since you want it to be the smallest possible c value, you'll set c equal to negative ma. So substituting that back into the equation we had before, the absolute value of e to the nth degree of x is less than or equal to mx minus ma, where you can undistribute the m, and you'll get the absolute value of e to the nth degree of x is less than or equal to m times x minus a. So you're going to want to repeat what we just did and take the integral of e to the n of x, e to the nth degree of x, where the same principle from before applies, where the absolute value of the integral is going to be less than the integral of the absolute, less than or equal to the integral of the absolute value, which will be less than or equal to the integral of now m times x minus a dx. We'll take out the middle term again because the integral is much easier to do without the absolute value on the inside. So we'll have the absolute value of the integral of e to the nth degree of x dx is less than or equal to the integral of m times x minus a dx. And when you solve out this antiderivative, you'll find that the absolute value of e to the n minus 1th degree of x is less than or equal to m times x minus a squared all over 2 plus c, because again, this is an antiderivative and not an integral with bounds. Again, we're going to need to solve for c, and we'll do this again by plugging in the point where the error is 0 at a, which will lead us to the absolute value of e to the n minus 1th degree of x, of a, is less than or equal to m times a minus a squared over 2 plus c. And with this, the error will be equal to 0, and a minus a will be equal to 0. So you'll just end up with c is greater than or equal to 0. And again, with the smallest c value, c is equal to 0. So here, we'll now have that the absolute value of e to the n minus 1th degree of x is less than or equal to m times x minus a squared over 2. And from here, we'll find our general equation, where the absolute value of e to the e of x is less than or equal to m times x minus a to the n plus 1th degree over n plus 1 factorial. And we jump to this equation because the degree of e added with the degree of x minus a is always equal to n plus 1. And so where the degree of the function e is 0, the degree of x minus a in the numerator will be n plus 1. The n plus 1 factorial in the denominator is found by thinking about the steps of repeated integration. As the degree of x minus a increases, the denominator will be multiplied by integers increasing with the degree. In the previous step, we saw that the denominator become 2, and if this result was integrated again, it would be multiplied by 3, and so on. This all means that if we know or are able to find the max value of f of n to the n plus 1th degree of x over the closed interval a to b, we will be able to bound the error of the nth degree power series centered at a for f of x.